Fortunately, this was preliminary stuff. Okay, can you see my screen now? Can you hear me now?
Yes, sir.
Okay, so you bring the notebook to life, choose export to HTML, and this behavior is normal. It's saying, what do you want me to do with it? Do you want me to clutter up your computer? And I choose yes. And now it is loaded in my local downloads file. To put it back onto my server, I'll put it right there. And to put it back on the server that you guys have access to, I will use the miracle of the Git utility. I'll add that to the repository, commit it, push it to the central repo. At some point, you all should teach yourself how to use Git commands in later classes. It will make your life way better. It actually give you the ability to find the professor's source materials and get to it sooner. Let's see, username. I mistyped something. Okay, so it claims the push was successful. And now we will go to your server that you're using in class. And you got the right user. And now everything is synchronized between 3 different machines all over the planet. So let's go to our lesson 21. So the title of the lesson is Prediction Engines, aka Data Modeling by Regression, and we're continuing it. And the subtitle is a little bit of marksmanship. So our objectives, as usual, are to apply fundamental concepts involved in data modeling and regression. Keep in mind, we're always asking, is a single variable a good estimator of the target process? Keyword here, target. And what kind of errors do we deal with? The computational thinking concepts that we're exploring are still abstraction and pattern recognition. The textbook that nobody reads is still mostly chapter 15. And let's start with an example. Suppose we are programming up a first-person shooter game named Olympic 10-meter air pistol. And we're going to develop it for use as a training tool for people that are going to compete in Olympic 10-meter air pistol. Because we don't know what that is, let's go to Wikipedia and learn all about air pistol. So it's an Olympic shooting event governed by the International Sports Shooting Federation using 4.5 millimeter air guns at 11 yards. And there's all sorts of stuff, tells all about the equipment. And you can see that in the case of air pistol shooting, it's good to put an eye out because you get better. That's a joke. And just for grins, who are we building this for? If we look at current world champions, we'll notice that India is a very well represented nation in air pistol. As we look at world champions going back several years, you'll notice a lack of United States champions. So even though we're good at shooting up shopping malls and schools, we're pretty terrible at Olympic 10-meter air pistol. So that kind of went the wrong direction. It was supposed to be funny. That was kind of cruel. So the U.S. hasn't had a world champion since the 80s. And I think it's just really cool that these other nations are dealing in air pistols. So, okay, so we've been contacted by our national leaders saying it's not acceptable that the last 2 American flags on this chart were back in 1979. We need some up here in the 2020s. So as part of our training mission, we're going to build a training tool. And to get started, here's our training tool. Since we are skilled Python programmers at this point, we know to import everything that we can think of. And so we'll import random, NumPy, and matplot library. And next, we're going to build a function. And this function is called showMyTarget. Not a very elaborate function name, but in our development process, we build the pieces, get them to work, and then during the refinement step, we'll go back and tidy everything up and make it work such that we can sell it to the United States Sports Shooting Foundation so they can use it to train their champions, future champions. So the function here is somewhat unremarkable. It's going to create a figure, and it's going to size it 10 by 10, so that makes a square. And on that, we're going to put 8 circles. We'll have a circle of diameter 1, colored black, another circle of diameter 1, colored orange with the fill turned off. So that's going to be a ring. We have another ring, diameter 1/2, a ring at 2, a ring at 3, a ring at 4, a ring at 5, and a ring at 6. We will set our limits so that our picture ranges from -10 to 10 in the X direction, -10 to 10 in the Y direction. We will give the ability to plot the location of any hits that we get on this target. We're going to plot them as red. And then we're going to add all these circles to the plot and finally show the plot. So if we run this, what do you think is going to happen when I click on run? Any ideas? It's an easy answer.
We're going to get a graph.
It's not going to do a damn thing because we just defined a function. That's what's going to happen. So let's discuss the concept of accuracy in both Olympic 10-meter air pistol and in our statistics or engineering context. Accuracy is a word that we use to describe or to measure how close to the true or population value is our estimate. Accuracy is the word or the term of how close we measure how close we are to the bullseye when we're shooting these Olympic air pistols at a target that looks somewhat like the figure on the screen. So let's consider the simulator below, because again, we're on our way to building a simulation tool that we're going to sell to the Shooting Sports Foundation for oodles of money, by the way, because they pay big time money for this kind of stuff. It might even be enough to pay for a cup of coffee by the end of the week. So here we have a target below. It's the picture centered at 0, 0. We're going to take 10 shots and evaluate our performance. Now let's suppose that we're kind of old and shaky, and sometimes we hit the bullseye and sometimes we don't, but over 40 years of shooting, we've gotten to where we're getting good scores. And we will represent our ability to put the pistol on the target with mu, which is where we tend to hit on average, and we'll represent our ability to hold the device steady when we trip the shot by sigma. If we were getting really precise in a competitive shooting, we would actually have 2 more metrics, which gives us how shaky we are because we're not doing our breathing right, and how shaky we are because we're twisting our wrists slightly as we trip the shot. But we're just going to glom all that into this one thing called sigma. And so mu and sigma conceptually have the same meaning in shooting that they do in statistics. They represent the measure of central tendency and how wobbly we are about that measure. Then we're going to take our 10 shots. In our case, we're going to sample our 10 shots from a Gaussian distribution with mu and sigma. And so our x value will contain 10 samples from that, and our y value will contain 10 samples. And you'll notice how we're constructing it. We're using a for loop to construct the samples, and then we're using the append feature on these two currently empty lists to store those results. And we're actually going to compute a distance of our xy coordinates to the center of this target. So perfection would be a red dot right smack in the middle. But we're humans, so perfection is pretty hard to achieve. And so let's go take our 10 shots. We do it. There's our 10 shots. And if you were diagnosing your shooting, this up-down stringing is usually characteristic of poor breathing. Ours is a complete simulation model, so we don't really know why it's doing that. And if we produced a histogram of the mean distance of the distance from the bullseye, we would get these different bin values. So that was our shooting metaphor. Now let's imagine that we go into a shooting game where instead of making 10 shots, we get to make a bunch of shots. Let's take 10,000 shots. Other than that, we won't change. We're very well fed and hydrated so that our measure of central tendency doesn't change, and our steadiness factor stays at 0.6. Go ahead and take 10,000 shots. And at this point, you actually couldn't score this target in the competition because we completely obliterated the center. Now, if you were North Korea, that's what you would like your home-built missiles to do to the United States, where the United States was that center black dot, because then you would have achieved North Korean nirvana and finally remove the evil empire from the earth. However, it would take 10,000 missiles, and they can only build 3 a year right now. So y'all don't need to lose sleep on that. Okay, so that would be our first exposure to the idea of accuracy. And notice if we take 10,000 shots and we produce a histogram of the distances of our shots from the bullseye, our histogram is starting to look like something. What's it look like to anybody who's feeling frisky enough to unmute themselves and answer?
A normal distribution.
That's a good guess.
Would I say it's skewed to the left?
Okay. What other distribution have we examined that that doesn't go below 0?
Gaussian?
No, Gaussian and normal are the same. We've only had 3 if you include Gaussian. So it's the third letter of the Greek alphabet is the name of the distribution.
Gamma distribution.
Yep, this is starting to look like a gamma distribution with a measure of central tendency at about right here, 0.7-ish. If we allowed negative distances, this would be well approximated by a normal. So the skewing of it is the restricting of it to positive values is what makes it a gamma distribution. For what it's worth, a normal distribution is a special case of gamma. Not true. A normal distribution is a regular distribution, so is a gamma. There's special cases of certain kinds of exponential construction. Okay, that's beside the point. So there's our 10,000 shots, pretty much obliterated the center. We're really happy. Now let's say we take our competition pistol, we put it in the box, and then we airship it to our next competition. The baggage apes, or what are known as baggage handlers, but I think the first term is better, see the box and then realize that, oh, the plane's about to leave without this guy's luggage. So the one on the ground grabs the thing and wings it up into the aircraft. On the way going through the loading door, it hits the side, then it hits the top of the baggage cabin and then bounces around a bit. And finally, the guy in the airplane doesn't want to quite reach over and pick it up, but he can just get it with his foot. So he gives it a stiff kick and it goes into the baggage net. In doing that, it's damaged our device slightly, such that if we use the same site settings, it's somehow been adjusted that it's now going to hit the measure of central tendency is going to be moved away from 0, 0 to minus 1.4, minus 1.4. Roughly, essentially, we've changed where the point of impact is by letting a baggage ape handle it. So remember, our desire is to hit at 0, 0. In the case of statistics, our desire is to get the correct measure of central tendency. We'll take 10 shots, evaluate our performance. Again, we're still a little bit sloppy and shaky, but we've been doing this for 40 years, and so we tend to get good scores because we're still in competition. And after the baggage apes has had their way with it, there's our 10 shots. And now we have what appears to be a problem. Something has changed with our accuracy. We go ahead and take the other 9,999 shots to get to our 10,000 shots, because in the training period we have the ability to do that. So we shoot that. We look at our histogram. Two things have changed. Now, what type of distribution does this look like? Whoever said normal, that this one's starting to look like a normal distribution. Our mean distance from the bullseye is almost 3 now. And in our prior one, the mean distance was a little bit over a half. People cannot read their damn calendars. I'm going to take a short, oh good, it stopped. Never mind. So we've pretty much have the same obliteration cloud, but it's no longer obliterating the center of the circle. If we use the North Korean removing the United States from the face of the Earth example, these are all the missiles and they landed smack dab in the Pacific Ocean. Pretty hard on the sushi trade, but most of North America survives. So those two pictures are pictorial representations of what's meant by accuracy. We were using the target shooting as just a motivating example, but it could be that what we're trying to estimate, our target could be the mean value of the population or some other metric. So let's suppose it's the mean value of the population. Which of those two pictorial estimates, in your opinion, would be a better estimate of the mean value of the population? The upper one or the lower one? The upper one or the lower one?
The lower one.
If the true value of the population is 0, 0, it would not be the lower one. The upper one would be the best estimate if the true value is 0, 0. Now, if indeed the true value is minus 1.4, minus 1.4, then the lower one would prevail. So the point we're trying to make is when we're doing estimates of unknown populations, our goal is to try to get the cloud on top of the dot. We have the extra added bonus feature that we don't actually know where the dot is. Our next concept that comes up in common talking is the concept of precision. So accuracy is how close we get to the real target. Precision is how repeatable is our estimate. In this context, the measure of precision is the dispersion or the variance or standard deviation, if you will. So we'll go back to our target shooting example. In this case, we will actually not intentionally, but we go on another airplane flight and the pistol gets knocked around again. And so our hit location is way off now. It's at -4. And remember how steady we used to be, 0.6. Let's say we struggle real hard because we don't know that the pistol's shooting at -4. And so we make some adjustments and we take our 10 shots. And now we see, well, that's a pretty tight collection of hits, but it's way off target. In terms of precision, if we take 10,000 shots, that's a much smaller blob than we had up here. So our tool, our ability to shoot the pistol, our precision has increased, but our accuracy still sucks. In terms of our distributional nature, the mean distance from the bullseye has moved a bit, but as we increase the precision, this histogram is going to get tighter and tighter. And since this is a game, we can easily increase the precision. Let's say we increase our precision metric tenfold. We get 10 times more precise, and it's practically a single dot. And I would assure you that a 10-meter competitive shooter would really love that picture as opposed to the prior picture. We haven't done much for our distance from the bullseye, but now our distribution gets narrower. And let's make this really good. We'll make the hole smaller than the projectile. And narrower still. If you look at the horizontal axis, 5.645, 5.66. And now we'll go back to our original precision, 4.5 to 6.5. So you can see the effective position of precision is to narrow down our range of errors. This histogram is representing errors, distance from the bullseye. Now if we adjust our sights to hit a little bit high and a little bit to the right of these red dots, and so we adjust them back up and back to the right, and then reshoot. Our precision is a little bit high there. Let's go back to the original 0.3. We make some adjustments, and now we're dropping everything in the black dot. So that would be a 100 point. 1, 2, 3, 4, 5, 6. 100.7, actually 8x, because that one's on the line, so it goes in. 108x, which would be a very good score in 10-meter pistol. Might even be a winning score. Although nowadays those Indian competitors and the South Koreans, they're turning in scores of 109x. They're only missing the bullseye by a single shot. And there's our distribution. If we increase our shot count, so if we increase the shot count, we change nothing. We're just taking more shots, and we've still obliterated the bullseye, but we've done less collateral damage. So if our shooting game represented, let's suppose our black dot represents cancer in our brain that we want to make go away. And one of our tools is to shoot it with a gamma radiation. So we have two radiation treatment instruments. We have this one, which clearly removes the offending cells, but kind of takes a lot of other cells too. And we have this one that also removes the offending cells and takes a few other cells. If you were having electronic brain surgery, which of the two pictures would you prefer, given that the target represents your brain?
I would say the bottom one because it has a higher precision than the first one.
I would prefer the bottom one also because it leaves enough of my brain left to be able to do stuff like drool and walk, whereas the upper one, while it indeed treats the injury, it also causes collateral damage. So so far, these have been very morbid examples. That wasn't my intent. This is a fun, happy day. So, so there we are. So we're now in our more precise, fairly accurate shooting. If we can increase our precision, let's say by a factor of 10, rerun the simulation, that would be a beautiful score in competitive shooting. And look at our histogram. It still looks gamma distributed, but look at our mean distance from the bullseye, 0.003. So this mean distance from the bullseye is somehow related to both our measure of where we tend to hit and our measure of how steady we are. The next concept is called bias. And bias is a systematic error or offset, similar to the distance from the bullseye in our example. For example, if we have a precise rifle that shoots a known distance from a bullseye, let's say we have that tool, even though that particular set of 10,000 shots isn't very good from a competitive shooting standpoint, it doesn't mean we want to throw away the tool. Actually, what you want to do is convince someone, oh man, you got a lousy rifle. Why don't you let me take that piece of junk off your hands? Because I can take it home and adjust the sights to correct for the bias, which is this distance from the group of estimates to the bullseye. You can either adjust where you aim the device or modify the device to account for the bias. And it's akin to the last example where we could demonstrate the contribution to error from a poor point of aim and an unsteady hand. So bias is not an evil thing in data. In fact, bias in some context is desirable because if we know there is a systematic error, we can deal with that. A lot of natural resources data that's collected in real time, the instruments that collect the data are known to drift. So like water level stuff that Farang's has talked about in the past, those instruments themselves lose their zero, if you will. They lose their mu value in our shooting context. Yet the data they collect, even after they've lost that zero, is still valuable because it's known that the rate that zero drifts, or the amount that zero drifts. And so when you go make a site visit to download the data from the data logger or to correct for the bias, you do a manual measurement with an independent device, and that offset at that moment can be computed into all the recordings, and you can correct for the bias, and you now have good data. And that is one of the data scientist's field job. Most people don't think data scientists get out of the office, but they do. Because if the data is not good, you got to hit it with a hammer. Our next concept is the term residual, and you've seen that already. In the context of our target shooting game, residual is simply the distance from the target that our model, the rifle, the pistol, places the estimate, the shot. So again, back to the first-person shooter analogy, our model is the shooting device, a 10-meter air rifle, 10-meter air pistol, and we're going to send an estimate, which is the projectile, and we're trying to estimate with that device where the bullseye is. If we do a good job, we make a hole in the bullseye and we win the prize, and we get the free coffee latte from the match organizers. If we don't hit the bullseye, we don't get the first prize. Instead, we have to go and make the coffee latte for the winner. Because in international competitive 10-meter shooting, that's pretty much all you're competing for, is bragging rights, and maybe somebody will bring you a cup of coffee. So let's examine the simulations all over again. First, let's do a set of shots where we have systematic bias. So we're not on our mark of 0, 0, and we're a little bit unsteady. We do that, 10 shots, and we're off here, we're low and to the left. And if we will use these guides on the axis, we're 5 units low, and we're almost 4 units to the left of where we want to be. This histogram, the distances from the bullseye histogram is showing us that same information. We know we want to hit at 0, 0. And that histogram is actually a plot of the residuals, of the differences between the model, red dots, and the true value, black dot. We could make many more shots, and all that happens is we get a cloud there, and there is our histogram of residuals. And now remember, last time in last lab, Farhang asked you, what did the residuals look like? And I'll ask you the same thing. I stipulate that that blue histogram is a histogram of residuals, where our estimates of the red dots are shots, and our true value is the black dot, our target. What can you tell me about those residuals, just from looking at the picture?
Would it be that it's 5, I don't know the measurement, but 5 away from the where we want it to be?
Okay, so we have a bias of 5.6 units. How do they look distributed to you? Abby, what kind of distribution does that look like to you?
It kind of looks normal, but I can see it's kind of skewed to the
Okay.
right.
So if it's kind of normal and kind of skewed, that distribution has a special name.
It's gonna be a gamma.
No, actually, I was picking on you. It was going to be Abby normal. So that's an Abby normal distribution.
Oh, okay.
These residuals are, because we don't have much information coming down here to 0. If we were to apply a normality test to these residuals, we would discover that the probability that a normal distribution can describe this is really high, probably like 0.96 or something. So these residuals would appear to be normal in any kind of test we can apply. Let's just see what happens if we do a few million shots. Okay, so we're basically in using all the, where did I do that? Oh, see, there's what happens when you take a million shots, is it takes a long time. Oh, that was stupid. I think I just clobbered my oh, I shouldn't have done that.
You broke the program.
Well, no, it's running right now. So there we go. We did a million shots. Now what does the distribution look like? It's normal. Yeah, it's normal. And then if we played with the histogram, we'll just jack up the number of bins and we'll let it run. We will be patient. I'm not on the class server, so it doesn't matter if I break the program today. And notice with a million shots, we're actually pretty good. We only have 1, 2, 3, 4 that don't touch the other ones. And any moment now, we should have our histogram. Now, what does our distribution look like?
Looks kind of normal.
Yeah, that's clearly an Abby normal distribution. And we didn't do anything different. We just represented the histogram with a different bin count. We had 1 million samples to pick from. But I assure you that in a competitive marksmanship, they won't allow you to shoot 1 million shots at a target because they don't have enough years to wait for you to get done. You're basically doing it with up to 80 is a typical competitive match. So you get 80 tries to get that histogram as tight as possible. So now let's modify our case where we know that we were supposed to hit at 0, 0. And so we turn some dials, get some incense out, sacrifice a few beanie babies to the gods of marksmanship, and put on our lucky shooting shorts and try again. And so what we do when we do that is we finally get our center about right. Our dispersion is still not as good as we can do. So this particular 10-shot group would be scored as 109X. That's actually a very good group for competitive air rifle marksmanship. And if we look at our residual histogram, most of our residuals are contained right here. A mean distance from our bullseye is 0.28. And we can look at another measure of the histogram called dispersion. Our mean dispersion from our point of aim is 0.16. So even with perfect aim, because we have shaky hands, our average distance for the target in that instance was 0.28, and our dispersion from that point of aim was 0.16. So let's try to improve things a bit, and we're going to put this thing into a vise, a mechanical mount. So now we're getting as much human element out of it as we can. When we put it in a vise, we get our point of aim perfect, and our vise is really steady because it's rigidly attached to the Earth. Unfortunately, the Earth is spinning through space at 800 or 900 miles an hour, and somebody 3 continents away opened the door and jumped out of their car onto the land, and that vibration is propagated as a shear wave across the planet to where we're making our shots. So we can't get our sigma quite to 0. We take 10 shots from a mechanical device, and frankly, our Olympic caliber target shooters would be really thrilled with that if they could do that freehand, because that would be a perfect score in the game of marksmanship. And if we look at our residual distribution, visually that doesn't look very good, but when you look at the horizontal axis, we're really close to the center point. Our mean distance from the bullseye is 0.01. Our dispersion from our point of aim is 6 parts in 1,000.
When it says dispersion, does it mean like what does that mean?
It's the standard deviation of the distance.
Oh, okay.
And so anyway, we're essentially on target, and we have a very tight estimate. So if you were to propose an interval estimate, let's take a few more shots so you have a picture to work with. Good shooting there. Okay, so there is our residual distribution. If you were asked to estimate what's the average distance from the bullseye at a 95% confidence interval, or what is the 95% interval estimate for distance from a bullseye, just looking at eyeballing that, what would that interval estimate be?
Would it be 0.005 to 0.025?
Okay, yeah, something like that would be. I wasn't particularly interested in the actual numbers you picked, but you correctly surmised that there'd be something here on the left and something here on the right, and we're excluding 5% of the blue area. we're keeping 95%. I think in that particular instance that I just suggested to you, our interval estimate would actually be 0 to somewhere out here because of the skewness, and that we have no negative distances allowed in our model. We would do what would be called a one-tail estimate. So we'd go from 0 up to maybe 0.027, and we'll save that for some other time to actually do the calculations. What if I restated that as a 50th percentile interval? Now that gets trickier, but 50th percentile, you want to exclude 50% of the blue area and keep 50%. And obviously you want to keep the 50% that has your tall values in it. So the 50th percentile interval estimate will be somewhere in here. The mean distance is 0.005 to maybe about 0.015. So that's the idea of interval estimates. If I want to get a 99.999999999% interval estimate, what's that going to be? Somebody unmute themselves and just state it, because you can do that by looking at the picture. %.
It would be from 0 to, let's say, 0.035.
99.9999. Go a little bit further to the right.
Oh, 0.04.
Yeah, 0.042. 99.999999 is pretty much everything we see is in that interval estimate, and there's probably more off to the right. But anything between 0 and 0.4 is very likely to contain the mean distance from the bullseye for any 10,000 shot collection. What makes things especially fun is if the target itself moves. And so this is just throwing gasoline onto a fire. So let's suppose the target moved, because everyone knows it's hard to hit moving targets unless it's in your computer. We'll start with our shot adjusted to hit minus 2.5 away from 0, 0, and moderate shakiness. And we'll take 10 shots. And what we've now done is we've adjusted where the target is. We moved target to -1, -3. We do that. There's our shots. In fact, we can make our shooting really good. And we're hitting at the right place, 0, 0. We have a very precise shooter, so we'll go ahead and do that. And we're not getting anywhere near the target. That's what happens when the target moves. And so to adjust for the moving target, which is now centered at -1, -3, we would have to mess with our mu. And because I'm doing this as a one-dimensional Gaussian distribution, this is actually a little bit hard to do. So we could slowly work our way in. And only if we get lucky would we actually be able to hit the target, because we actually need another adjustment here in the XY coordinate. But you get the point. As the target's moving, we can look at these residual plots and see that they're staying roughly normal, but they're wobbling on the x-axis as we try to get in on the target. Okay, so to summarize, before I move on to the next topic, which is a continuation of last time, when we're making estimates from our sample, of a population parameter. How close we are to the true value of the population parameter, which might be unknown, is called the accuracy. So that's the accuracy of the estimate. And we have methods to estimate the accuracy of the estimate. We usually call those interval estimates. And we looked at that before. When we make an estimate from a sample of a population value, and our estimate is always wrong by a fixed amount in sample after sample after sample, we have a biased estimate. Bias is not bad unless you can't detect the magnitude of the bias. Then we have no way to proceed forward. If we make estimates of a population value over and over again, and those estimates are all very close to one another, we have a very precise estimation process. If that precise process is also biased, and we know the bias, we would end up with an accurate, precise estimation process. We'd have a place where our little red cloud completely obliterates the target the way we want it to. If those are not true, then all the statements are not supported. So the prediction estimate that you were shown last time, and you'll get some study on it today, is an attempt to quantify how close our sample estimate could be to the true but unknown value based on the variability of the sample estimate itself. And so we're using all the ideas of target shooting in our regression analysis. All right, let's revisit our multiple listing service regression from last time. Let's suppose we're tasked with the following. We want to relate the abrasion resistance of rubber, which is indicated by the variable y, to the amount of silica filler, which is indicated by the variable x sub 1, and the amount of hardener, variable x sub 2. So we're fabricating an artificial rubber for some industrial use, and our factory people have discovered that fine particle silica fibers increase the strength and abrasion resistance, and the hardener is what chemically bonds the filler to the rubber polymer chains and increases the efficiency of the filler. The units of measure are parts per 100 of rubber, which is a weird unit, but it's common in industry. A unit of parts per 100 or parts per 1,000 are weird to us, but it's quite common in industry. And so before we commit to silica fiber and hardener adjustments, because one of the principal things in manufacturing is if we're making it and we're still selling it, we don't want to hurt that cash cow. So there has to be good reason for switching a process. So we did get permission from the boss to make some experimental runs on weekends and run the factory with different amounts of silica filler and hardener added to our process. And then we measured the abrasion resistance of rubber with some device that we have been using manufacturing in the past. And the units of the abrasion resistance measure are unstated in this example. So for example, if we put 1 part per 100 of silica filler and minus 1 part per 100 of hardener, so I guess we remove the amount of hardener that was there, we get a resistance of 83. If we add 1 silica filler, 1 hardener, we get a resistance of 113 and so on. So that's what this table is conveying to us. Let's examine a couple of models and simply assess their utility to explain these data. So we're going to do data modeling. We're not going to do any sort of chemical or other modeling to attempt to understand any physics or chemistry of this process. We're simply going to model the addition or removal of different components in our mix and see what the abrasion resistance. So that is one way to do product development. And let's further stipulate that we have two models that we can consider. We have model number 2, which is y is equal to beta 0 plus beta 1 x1 plus beta 2 x2. It says the abrasion resistance is equal to some constant plus a coefficient multiplied by how much silica fiber is added, plus another coefficient multiplied by how much hardener is added. And we have the ability to have negative and positive hardener values. So think of these as changes from some standard mix state. What can you tell me about model 2 just based on its mathematical structure? What are the variables in model 2?
Beta 0, beta 1, beta 2.
Are those the variables or are those the coefficients of an equation?
Oh, the coefficient.
Good. What are the variables?
X1 and X2.
X1 and X2. Is that equation in a fine equation? A fine is a fancy word for, is it a equation that's linear in the coefficients? In other words, is y a linear combination of beta 0s, beta 1s, and beta 2s?
In the first one it is, on the second one
Okay,
it
I
isn't.
haven't asked about the second one yet. Correct. Yeah, the first equation number 2 is listed here is linear in beta 0, beta 1, and beta 2. Also happens to be linear in x1 and x2. Let's look at this at equation number 3. Equation number 3, we have equation coefficients beta 0, beta 1, beta 2, beta 3, beta 4, and beta 5. And beta 1 is the coefficient that multiplies x1, whatever the value of fiber addition change is. Beta 2 multiplies x2, whatever the value of hardener addition change is. Beta 3 multiplies x1 squared. So we look at the fiber count, we square it, we multiply that by beta 3, and we add it into our model. Beta 4 is x2 squared. We look at the hardener change, square it, multiply that by beta 4, add it into the model. And we look at the product of the two, fiber times hardener, multiply that by beta 5, add it into the model. So is that model linear in the predictor variables, x1 and x2? Is y some linear combination of x1 and x2? 50-50.
How do we tell if it's linear or not?
You tell me.
Well, because we have the square value, it's going to take on a quadratic form.
It's, yeah, this is not linear in x1 and x2. Is that model linear in the betas?
No, I suppose.
It is linear in the betas because all we're doing is we're adding beta 0 plus beta 1 multiplied by some weight that we get from x1, beta 2 times some weight that we get from x2, beta 3 times some weight that we get from x1, happens to be a function, beta 4 times some weight of x2, also a function, plus beta 5 times some weight of the product of x1 and x2. So this is non-linear in the x's, but it's plenty linear in the betas. So maybe that will help answer the earlier question, how do you tell if it's linear or not? You look at the terms of interest and you see if they are products of something products of themselves, or they are themselves raised to a power, or themselves arguments to a function. And the betas are not raised to any power. They're just multiplied by observations. So that model is linear in beta, nonlinear in x1 and x2. Well, if the model is linear in beta, do we have tools to estimate the values of betas that we don't even know what they are yet? Well, obviously, if I'm talking about it, that would be a yes. So let's go ahead and we're going to read these experimental data, and then we are going to construct a couple of models. We're actually going to construct these two models. So here's our experimental data. These are the abrasion resistance measures for the 3, 6, 9. I think there's 11 experiments there. These are the silica fiber additions, and these are the hardener additions. So 0, there's no addition. 1 is we've increased the amount. -1 is we decrease the amount. And to construct equation 2, we basically have everything we need. We have x1 and x2, but to construct equation 3, we're going to need x1 squared, x2 squared, and x1, x2. So we'll create room for that, and here we'll simply do the arithmetic. So what does that line of script do as we're building our experimental data streams?
You're making you're appending the x1 times x1 values.
Okay, and up here in this equation number 3, what column is that going to be used as?
It's going to be used for B3,
Good.
beta 3 x squared.
Good, you're correct. This next line, x2, x2, what does that do?
Beta 4 x squared 2.
Good. And then the last line, x1, x2.
Beta 5 x1, x2.
Excellent. So this list x1, when we go ahead and start to construct our model, will be used here in this equation and here in this equation. This list x2 is used here and here. This list x1, x1 is used here. This list x2, x2 is used here. And this list x1, x2 is used here. Now it's plausible that you could actually do the arithmetic as you're building the linear system to do your regression modeling. But I find it more clarifying to understand by creating these separate lists. Let's try to project our information in a 3-dimensional projection. So I hope this actually runs. I'm going to import from something called MPL Toolkits a subpackage called mplot3d, and from that subpackage I'm going to import a tool called Axes 3D. Then I'm going to import from matplot library pyplot as PLT and our friend NumPy, and then I'm going to attempt to plot our actual experimental data, our x1 and x2 values and our corresponding y values. So let's see if this runs today. Oh, good, it decided to work. And the only thing I wish I could do is make this plot bigger. But what I can do is I can just make the page bigger. So these red dots are now an attempt to represent our 3 dimensions of information. On this axis here is our x1 axis that represents our silica adjustments. This axis here, our x2 hardener axis. So this entire plane down here plane, like a 737, is the x1, x2 plane. And so if we look in our original data, our values of x1 go from 1 to minus 1.5. Our values of x2 go from 1, well, from 1.5 to minus 1.5. So we would expect this plane to go from minus 1.5 to 1.5, minus 1.5 to 1.5, and you'll notice it's a weird numbering. That's so this is going minus to positive from left to right. This one's going minus to positive from front to back. So normally we would be we are accustomed as human beings in two-dimensional plots that this whole set of labels right here that the cursor is circling around. Everybody who's still paying attention, you see that cursor circling? You're getting sleepy, very sleepy. Of course I am, Dr. Cleveland's talking. Normally that is plotted over here when we draw a graphic. But because we have this back wall here, we move it to the right. So this point right here where my arrow is pointing, in the x1, x2 axis, what ordered pair does that arrow represent?
Can you say again?
What ordered pair is my arrow pointing at in the x1, x2 axis?
-1, 5,
Five.
and -1, 5 as well.
That sounds right. Okay, you're correct. Minus 1.5, minus 1.5. So this plane down here has what we are accustomed to for a two-dimensional chart. And now moving up from the plane, we're introducing our third dimension, which in our case is the abrasion resistance factor. The abrasion resistance factor ranges from somewhere in the 80s up to 113. So we're going from the 80s to the 110s. And so for instance, this point right here is 1.0 minus 0.5. It's hard to visualize is my point. We've got these three dots right in here, which correspond to these three places right here, the 0, 0. Then we have some dots over there and then back here that are representing our different combinations of x1, x2, and their predicted value of y. So unlike what we're accustomed to doing, we can certainly render a three-dimensional representation, but what can we learn from that? What's the best way to increase abrasion resistance? We don't really know. So let's continue and try our ordinary least squares approach. In this case, we're going to use the stats model API as SM. We're going to use the ordinary least squares fitting tool and run the regression. And nothing will happen. Why is that? That was 33, 38. Okay, no module name stats models. That is going to be a problem. Let me get my thing working correctly. Squirrels are working slowly today. Taking longer to install than I expected, but I will wait it out. We are good on time. You're going to get to meet a couple of Olympic marksmen in lab today. They predate 10-meter air rifle, but they are surely, if they lived in today's day and time, they would be I would attempt to give it more resources, but I have all 4 CPUs are running at about 90% user. This thing's actually running about as hard as it can. And sadly, I think CPU 0 is the one that's currently dedicated to keeping this screen that we're seeing up and alive. So I can't do anything with it without losing the connection. And then all the builds are happening in the other 3 CPUs. And I don't know what you Windows users do when you need to monitor stuff. Because even the task mangler, it's hard to find this level of information that we have going on. So I'm going to wait for all the root processes to die, and then we should have a completed build. But I don't want to make any other changes in anything else, because I don't want to tie up the poor kernel having to keep track of work that is unnecessary. That's actually, I guess that stats model is a pretty big packet. It's been building for 1 minute and 35 seconds. Sleeping, interrupted. Dang. I'll let that build in the background and we'll come back to that. So if there were a module named stats model, we would have gotten the output, and we'll wait till we get back. And when we build our model, what we're doing with our linear model, this first one, we'll go ahead and we run ordinary least squares. We'll get a value of coefficients of beta 0, beta 1, and beta 2. And when we put those back into our model, that model is simply this plane. So those red dots are just the plane that's represented by the model. So if we decide that our equation number 2 is our bestest model, that plane defines where all the predictions are going to be based on any combination of x1 and x2. It predicts the abrasion resistance factor. Now keep that picture in your mind right now, Okay, so I need everybody's short-term memory flipped on. It's like you're memorizing a phone number for somebody you met at a beverage delivery facility that you're hoping to call later on. Okay, that part of the short-term memory. So you got about 10 seconds. And then ask yourself, how well do you think that plane fits through those actual observations? And at this point, all you can assess is good or so-so, because we don't have anything to compare it to yet. What would be nice is if we could plot those red dots in a different color through these red dots and visually assess how well that or poorly that plane explains those observations. Next, we can take our next model. I'm not going to attempt to run it because it'll clobber it. And we'll predict it on our 5 variables, x1, x2, x1 squared, x2 squared, x1, x2, the cross term, and the constant. When we do that and we make our model that has 5 predictors and then replot it in our 3-dimensional scale, our equation 3 data model is this curved object. So it's curved in 2 dimensions. It's curved in the x1 dimension, curving down, and in the x2 dimension, curving over, and in the cross dimension, a slight upward curvature. And then again, if we can plot that with the original picture, we could visually assess how well that model explains our data versus the first case. How else can we assess how well our model fits the data? Any ideas?
We can
Could we
look
use
at
another? Could we use another thing like WLS or MLE?
We could, although this is incorporating it. Do you remember anything that Farhang introduced you to lab, our last lab on Tuesday? Now that's long-term memory, so flip off the short-term, go retrieve the long-term just between the episode of Dance Moms and Drag Race, and see if there's anything in that picture that suggests how you might quantify the model's utility.
Well, we can look at the R-square value, and it tells
Excellent.
us.
Okay. We can use a goodness of fit measure. So in that one, it has an R-squared value of 0.915. Remember also what he told you about R-squared. It's not the whole story. There's quite a few other ones. And in this one, which we can't see yet, I think that is stalled. But we did make I think we made a PDF copy, didn't we? We did. Let's look at the PDF. Everything's there and get past those little shooting pictures. Everyone loves shooting, right? So there was our first case. So here's our model 1. This was our first one. Beta 0, beta 1, x1, beta 2, x2, shown in beautiful latex typesetting language because it refused to typeset it. Thank you, computer. And the R-squared for that model was 0.147. So for the sake of discussion right now, let's pretend R-squared is our metric of goodness of fit. Our R-squared for the next model is 0.915. So using those two as measures of goodness of fit, which is the preferred model if R-squared is indeed the metric of awesomeness?
The second one?
Yeah, the second one. It has a much higher R-squared. We would be foolish to just stop there. What we'd want to do is plot that with the actual original data in the plot rendered in different colors to see how well it's doing. So what were some of the other measures of goodness of fit that Farhang mentioned to you?
Mean absolute error.
Mean absolute error. How would you compute that with this model?
I guess you might have to get a list of the predicted value.
Why not take the residuals list and compute their mean, because that should be the same thing, because the residual is just model minus observation. So there is a residuals list that's generated, and we would extract it from the results object. What's one of the other measures? What you said was correct. If you can't find the residuals list, it would be trivial to simply code up the model and then take differences between the model and the observations and then compute the error based on that. What other measures of error?
It was mean square.
Mean square error. How would you obtain that? Two ways.
Square the mean.
One way to get the mean squared error or the squared error would be to code up the model, predict abrasion resistance from your data model, compare that to abrasion resistance from the actual observations, take those differences and square them. That gives you your squared error. And then if you want to make a mean, what do you do next? You've squared it up. How do you make a mean?
Would you divide it
Divide
by the
what?
total sample size?
Okay, so now you've squared them up, and you're going to divide 11 things by 11. So how do we get the mean value, though? You're halfway there. You guys aren't thinking clearly. You're halfway there. What's the mean of anything?
The average.
What's the average of a collection?
It's the summation of your x values divided by the number that you have.
Right. So we have just computed 11 differences between our model and our observations. We squared them. So now we have 11 squared differences. And then we do what Abby says. Let's just add them all up. And so now we have a sum, and then we divide by how many of them there are. So that would be your mean square error. Now that we have the mean square error, what's one other metric that we explored? Take the root of the damn thing. That's the root mean square error. So you have several measures of goodness of fit. Let's see if I have my computer running again. Sweet. Okay, let's go ahead and try to run this. You piece of crap. Oh, it's not done installing.
I have one question. Regression, like you said, is the observed minus the prediction, right?
That's not regression. That's a residual.
Okay, thank you.
Well, until I can regain control of my computer, running as root. My Jupyter Hub is singing. It is seriously annoying me. Well, this process right here is stalled. I wonder if it's the same as this process. Yeah, I bet you it's 549830. We may be done with me today. Yeah, but I think we got to reboot everything. That's screwed up. Okay, let me, we actually ended up at a good ending time, and you can now take a few minutes break while I hand off control to Farang, and you can get to meet Daryl, and who's the other character they're going to meet today?
Horace.
Daryl and Horace. You're going to like these guys. They wish they could have competed for world championships.
So we are running a little short on time. So I will begin right at 11:30. So 2-minute break. Sorry, guys. Okay, it is 11:30, so we are going to begin our lab 20 on confidence in linear regression, or the exclusive guide to trial by combat in Vestros. So I understand that we have been spending many sessions, quite a few sessions on linear regression, but as you understand, the topic is quite important, and it's going to be very useful regardless of the engineering field that you're going to pursue in the future. So let's do a very quick review. What is linear regression?
Like
Come
a
out.
line to fit our data.
Come again?
Linear regression is like assigning a line to fit our data.
Okay, yes, so you're using a linear data model to provide a fit for your data. Why do we need that? Why do we use linear regression?
Because it gives us a way to extrapolate from population or from a sample.
Correct. And also,
Isn't it a way to do less work? That's how I think of it. Like
less
if you
work as in,
like if you're looking for a specific like point in the graph or like in this specific scenario, instead of having to recreate like the experiment or however you got your data, you can just use linear regression to find that.
yes, that is true, but that holds true for almost all modeling endeavors, including linear regression, correct?
Yes.
So that is true for modeling for the modeling part. Sean said to basically predict or extrapolate beyond the samples. There is one other reason.
To explore the relationship between the predicted values and the values you're given.
Exactly. Thank you very much. To basically get an understanding of how strong the relationship is and whether the relationship is linear, whether it is positive or negative, and stuff like that. So, how does linear regression work? How do we do linear regression? Nolan, are you there? Nolan?
Sorry, I
Okay.
was chewing. What's up?
Are you there?
Yes.
Cool. So my question is, how do we do linear regression? What is the format of the data model and how do we approach?
Oh God. Not sure.
Let me highlight the answer for you. So the format of the model is a line because it's linear regression, correct?
Yes, sir.
So the format is going to be our estimated y equals beta multiplied by x plus alpha. What is beta? What do we call that?
Mu?
No.
Sigma.
Slope.
Slope. Oh, mx.
And then
plus beta.
intercept for alpha, correct?
Yes.
So our goal is to find the best value for beta and alpha. Would you agree with that?
Yes, sir.
Okay. What values of beta and alpha would I call ideal? Would I call best?
The ones that minimize the difference between y.
Exactly. Between y and the estimations of y, which is basically our error. So yes, we want values for beta and alpha that gives us the best fit with the minimum error. Thank you very much. The next question is, how do we find those values? How do we find the best values for beta and alpha? Jalissa, are you there? Jalissa. Nope. Lane, are you there?
Yes, sir.
Okay. Can you help me with this question?
Sure thing. What is linear regression?
No, the question is, we so far we have confirmed that we need the best value for beta and alpha, the values that would give us the minimum amount of error. Now the question is, how do we find beta and alpha?
Sorry.
It's all right.
The mailman probably came by or something.
Yep.
Well, you got me. I'm trying to read here to see if there's anything that might.
So last session on Tuesday, do you remember what we talked about?
We talked about graphing a couple of things. We talked about a little bit about significance, I think, but not anything that I remember about alpha and beta.
Do you remember the part that we were talking about the movie Gladiator?
No,
Okay,
no.
that's a shame. It's all right. Don't worry
Sorry.
about it.
I like
So-
that movie too. I'm sorry.
It's okay. So let me see who else I can ask. Quentin, are you there?
Yes, I am here, but I like also I wasn't here last class.
Okay. Do I have anyone who was here last session and remember why we talked about the movie Gladiator?
I was here.
Okay.
So to find the betas, we use the formulas.
What
that we-
formulas? You're getting close.
Like for alpha one, we were giving like the summation of x1 minus the mean.
Correct, correct.
Just the
But
whole formula thing.
how did we get that formula?
How we got the formula?
Mm-hmm.
Then
There
we
was
took
a method.
we used the SSE formula. I think. No, we took the partial derivative with respect to the intercept.
All that you're saying is correct, but that fell under one giant method or approach that we used. And if you look at the chat box, the reason why we talked about the movie was the name of the main character, which was Maximus. So when I say Maximus, what comes to your mind?
MLE.
Yes. What is MLE?
It's where we use the known values and data we have to find unknown parameters.
Yes. MLE stands for maximum likelihood estimation. And that was the method that we used to get those formulas and to calculate the values for slope and intercept. Okay. Wally?
Yes.
Okay. Now, was that the only method? This is a question for the rest of you. Was that the only method that we have to get the slope and intercept? OLS. Aaron, yes. Can you use your microphone?
Yes, sorry, I was eating.
Okay. So OLS stands for?
The ordinary least squares.
Uh-huh. And when we used OLS, did we get different answers from when we used MLE? Or are they telling us the exact same thing?
I think we got the same thing.
Yes. And also true for what Wally said in the chat box. Yes. Going from OLS or MLE gave us the same estimates for alpha and for beta for slope and intercept. And we can use both methods for linear regression. And then the question is, how do we assess the fit? When we get the linear regression model and we, for example, get our plots and everything, how do we assess whether a fit is good or bad and whether it is better than another fit or not? Goodness of fit. One answer in the chat box. Anyone else?
We had several after that. So we had like the mean absolute error.
Mm-hmm.
And then in lecture, we talked about mean squared error and root mean squared error.
Okay, so these are goodness of fit measures or goodness of fit metrics that we can use to describe and assess the goodness of fit. Thank you. Was there another method that we have been even using before Tuesday? The Harper Hill method?
The visual goodness of fit.
And based on, for example, a graph, you would look at which ranges does your model perform better over or worse over, and you would provide a more visual description of your model's performance. So these are also the ways to assess the fit. 5 questions, a quick review. Do you have any questions? Okay.
When do we use OLS and when do we use ML?
Well, currently, and for the sake of this class, you can use any of them unless specified by the question.
Okay.
Okay. Now, do you remember this? The line of fit, the actual values, and then this difference we would call the error. So the difference between the estimated points by the model and the observed sample was the error. So the next question that we have is, how confident are we with a prediction? So we did everything. We found alpha, we found beta, we did the fit, we used our goodness of fit measures, and we know everything that we have covered up until the end of Tuesday's session. How confident are you with a prediction? And how do you base that confidence?
Are you asking us?
Come again?
Are you asking us, like, answer you?
Yes,
Or
I
is
am.
it rhetorical?
No, I am. I am asking for your opinions at this point.
So how confident we are with prediction depends on what type of method we're using. Like I said, we're using the R method. The higher the R is, the more confident we are with the prediction. But the lower it is, the less confident we are with the prediction. So it all depends on what type of method you're using.
So let's say that I give you 10 samples from. Okay, let's give you an example. We are using a new drug, and it is supposed to help with headaches. We ask 10 people to take the drug on the first trial. 9 of them take the drug and feel better almost instantly, like after 1 or 2 minutes, the headache is gone. 1 of them takes the pill, 1 minute passes, 2 minutes pass, and then his head explodes. So 9 out of 10, your drug is working, 90% accuracy, if you will. Would you be willing to take this to the next level?
Probably not.
Why not?
Because that one mistake is very bad and it could cause a publicity stunt.
Exactly. And quite more importantly, you may end up killing a lot of people.
Oh yeah, that matters too.
So, here's the thing. When you run the model and you get a goodness of fit metric, that is part of the story. The error of your model comes from these 3 elements. Variance, again, coming from the model. Bias, coming from the model. And then another kind of variance that comes from errors that are beyond your control. When I say errors beyond your control, what comes to your mind?
I guess values that aren't included in our baseline data, I would think.
Why?
Because I was assuming this in the experiment we're doing,
We're not in God mode. And because of that, we can't see or know every single possible outcome and possible confounding variable. So that would be what the variance and reducible error would be.
So because we are not in God mode, we need a model. We have created the model and we have fit it to our samples. There is a variance and bias coming out from that model that we can assess, and we will talk about a little more about. But when we say errors that are beyond our control, we are saying that regardless of what we do, there will always be some error. What are those? They will differ from case to case, but think of an example and then tell me what kind of errors are we talking about?
Is it things like a black swan event?
Explain more.
So like once in a lifetime events that happen during a kind of like the market recessions of 2008.
Okay.
No.
But that is still an event, correct?
Yes.
So do you remember the example where I would go to the river and make measurements of flow rates?
Yes.
Okay. So when I did go there, how did I make my measurements?
Didn't you have a machine that made them every day, or was it every year?
Okay, so I'm using a machine, right?
Yeah.
What units does that machine make its measurements in?
Wasn't it like gallons per? It was like was it the actual flow rate, like, or was it a measure, or was it? Oh boy.
Just give me a unit. It doesn't matter. It's your machine at this point.
We'll go with liters per minute.
Liters per minute. Okay. So when I go out there and I read 1, that means 1 liter per minute. If I read 2, that will be 2 liters per minute, correct?
Yes.
If the actual flow rate at the time of measurements is 1.5 liters per minute, my machine will not be able to detect that, correct?
Yeah.
It will either say 1 or 2.
Oh, okay.
So that piece of information, that little 0.5 amount, will be missed by my machine, correct?
Yes.
And whatever modeling that I do based on the outcomes of that measurements will inherit that error. And that is going to be beyond my control as a modeler.
Oh, okay. So it's kind of like calibration error.
That yes, that is part of the deal. Then we have human error. Maybe I go there and I read that data wrong. So it was actually 2, but I was drunk and I read it as 5. And
So,
believe me, that happens.
So it'd be like systemic error. Like,
Mm-hmm.
Oh, okay.
And these has nothing to do with the model that you create and design. This happens in many cases even before you begin your modeling endeavor. So these are the irreducible errors and the errors that are not coming from our model. Do we agree on this? Yes, go on.
For the shooting error we had before, would let's say wind be the irreducible error? You can't control at all, like wind. Like
pretty much, yes. If we assume that modeling the wind impact is not possible, then yes, you can say that. Any other questions about this? Okay. Now, I have a little story here for you. Let's assume that you were arrested by the King's Guard as you were minding your business in the streets of King's Landing for the crime of planning for the murder of King Joffrey Baratheon. As much as you hate King Joffrey, and I hope you do, you had no plans for killing him, but no one believes you. In the absence of witnesses or a confession, you demand trial by combat. And I hardly think that your demanding of trial by combat will be as cool as this guy's, but let's move on. They kind of inform you that the Germanic law to settle accusations is no longer used, and it has been replaced with a new method. You get to choose a bowman. That bowman will make 3 shots for you. If he hits the bullseye even once, you will walk a free man. Otherwise, you will be hanged. Do we understand the rules of the game?
Yeah.
Okay. Now, you have 2 options on that day. The first bowman is Horus. He is known as one of the greatest target archers of all time. He is old though, and due to lack of an efficient social security system in Westeros, he has to work as a hired bowman for the High Court to earn a living. You've asked around and you hear that he still can shoot a bullseye, but as his hands shake, he sometimes misses by a lot. The second archer is Daryl. He is also a well-known archer, but unfortunately he has a drinking problem. You have understood that there has been cases that he has shot the bullseye in all of his 3 shots, and there has been cases that he has completely missed the bullseye. The thing about him is that his 3 shots are always very close together. When you hear this, 3 shots close together, based on what you learned from Dr. Cleveland, what comes to your mind?
So basically, when we sorry.
Precision.
Precision for Daryl is what you hear. Wally, you wanted to say the same thing?
So basically, when we're picking between the 2, we're picking between accuracy and precision. Like, which one do we want?
Okay, that's one way of looking at it. Harper also said precision. Now, you get to pick between Horus and Daryl. Who would you choose to shoot for your freedom? Cast your votes in the chat box. I have 1 vote for Daryl by the brave Brandon, but the rest of you are voting for Horus. Another vote for Daryl. More for Horus. 3 for Daryl. 4, 5. Okay, Daryl is getting some popularity. I don't know why, but people tend to love drugs. So, I think no more votes is coming in. I want 1 from each team to unmute their mic and tell me why they voted for who they voted for.
I wouldn't vote for a drunk person just because they're unpredictable.
Okay, that had some strong ethical perspectives to it, but was that your only answer?
Yeah.
Okay.
I just voted for Daryl because he's the underdog, honestly. Just wanted to see an underdog story.
Okay. So Harper was the first one who voted for Horus. Why?
So you just need 1 bullseye. So I don't really care about your grouping or consistency. And with Daryl, since he has a great grouping, basically you get one chance to hit the bullseye because all the arrows are going in the same spot. With Horus, they may be all over the place, but as long as one hits, then you're good.
Okay, that's a fair argument. Brandon was the first one who voted for Daryl. Brandon, you want to share your thoughts? Okay, I'm going to ask the second person who voted for Daryl, who was Joshua.
So I think it was
Sorry, Dr. Cleveland, that was perfect. So sorry, go on, Joshua.
I just picked him because I guess I feel like because he's older, he's gonna be more efficient. I think I can't trust a drunk.
Okay. I think what you said was summarized in what Dr. Cleveland had said. Do I have anyone else who had picked Horus not because of his age, but actually because of his ability?
I have reasoning for picking Goat Horus. The reason I pick Horus is you get 3 tries, right?
Yes.
With Daryl, you only get 1 try. So you have a less likely chance to hit the bullseye. So if you miss the bullseye the first try, he's missing the bullseye for every single time. But with Horus, you still have 3 tries. You know what I'm saying? So Horus to me is the best likely option and will be the option.
Okay.
Unless Daryl for some reason isn't drunk that day. But he's always drunk, so it's fine.
So those who have voted for Daryl, do you have any statistical reasons why you've picked him? And don't come out and say it because he's hot, because he's not. So I'm not hearing anything, so let us move on. Let me see what Dr. Cleveland has sent. The Daryl that I was shooting for was the guy from The Walking Dead. I hope that at least some of you recognize that. So
where's Horus from?
Horus is actually an ancient Greek archer. Let me.
I thought you're going for the Egyptian one.
I think you meant the God one. Never mind.
The Egyptian one is spelled differently. Horus is the Egyptian one, and he is.
Well, I mean, it's spelled in hieroglyphics.
But the way it's spelled in English is Horus.
I gotcha.
It's this one, and apparently.
Greatest archer of all.
United Kingdom. He was British. Right? Yeah, this is where the name is coming from. Now, let us move on to bias, variance, and the Bowmen dilemma. We use the example above to give you an initial understanding of bias and variance and their impact on the model's performance. Given this is a complicated and yet important aspect of data modeling and machine learning, we don't want to get into too much detail, but it's always good for you to have some kind of understanding about it. So, bias reflects how close the functional form of the model can get to the true relationship between the predictors and the outcome. The true relationship between the predictors and the outcome will be the bullseye. Variance refers to the amount by which the model would change if we estimated it using a different training data set. These are official definitions of these 2 terms, but let's have a look at these 4. When we have low bias and low variance, we will be in a situation like this, which is quite ideal. When we have low bias and high variance, we will be in a situation like this. So you see they are more dispersed, and you do not have like a cluster. When we have high bias and low variance, our shots are close, but far from the bullseye. And then when we have high bias, high variance, we will be in a situation like this. We are far and we are dispersed.
So is bias basically the distance from the Q value?
I would say yes. So the way I usually look at it, I usually talk about it is, let's say in this case, we have like 10, 12 points. If you take the average of those points and you are close to the bullseye, you are dealing with a high variance model. So in this case, if you take the average, where will you be? Somewhere around here, right?
Yeah.
Is this a good point to be?
Yeah.
Okay. So you're dealing with high variance and low bias. In this case, if you take the average, where will you be?
To the right.
Somewhere around here, right? So
yeah,
even when you take the variance, you are far from the bullseye. That means that your model is also suffering from high bias. Is that clear?
Yes.
Yeah.
Okay. So between these four, which one is ideal?
Top left.
Low bias, low variance, that's ideal. Which one is the worse?
High variance, high bias.
High variance, high bias.
High variance? So
But wait, but for this situation, wouldn't we want high variance? I mean,
again?
for this situation, wouldn't we want high variance and low bias?
So that was a very good question. Let me ask two more questions and then I will come back to you. I told you in this story that you had two options to pick from. One of them was Horace, the other one was Daryl. Which one is Horace?
High variance, low bias.
Why would you say that?
Because he can still hit a bullseye, but he's gonna have high variability.
Exactly. So he has a chance of hitting a bullseye, but his hands are shaking. So every once in a while, he may get it far from the bullseye. Which one is Daryl?
High bias, low variance.
High bias, low variance. Why would you say that?
Because it says that his shots cluster together,
Mm-hmm.
but that he can still hit a bullseye. So it would be closer to the bullseye area rather than like the white outer.
Exactly. Thank you very much. Now, going back to your votes, going back to the story and looking at this figure, if you wanted to pick someone to save your life, who would you pick?
Horace.
Horace?
Let's go. Yes, go Horace.
Horace, because of the exact same reasoning that several of you made. Because you only care about one of your points, 1 out of 3 to be in the bullseye, and you will walk free. So basically, when you have a high bias model, your points are going to be very close to each other. So in this case, it really means that you have only one shot, because all of your 3 shots will go to the same place. If you hit, you hit. If you don't, you don't. You will know everything by the first shot. But with Horace, if the first shot is gone, you still have 2 chances. If the second shot is gone, you still have 1 chance. So you have a better chance of survival if you go with Horace. Is it always the case? Do we always want a model that has high variance and low bias?
Not always.
can you think of an example
An
where you
example
want?
would, an example is, let's say you're testing drugs. You
Mhm.
would want there to be low variance, but the bias wouldn't matter because you could manipulate the bias using, let's say you go back into the lab and fix it up. But high variability doesn't allow you to truly see how the medication works.
Yes. So in the example that Dr. Cleveland was using, let's say I'm developing a system. I don't want to use warfare. So let's say I'm developing a machine that sends artificial clouds to increase rainfall in a specific parts of the world. I test my first model and I get this result. So my intention was to get some rain in Lubbock. I did get rain in Lubbock in 3 cases. I got some rain in Amarillo, some in New Mexico, and some in Dallas. My second model on its first trial gave me 10 rainfall events, but all of them happened, for example, in hubs. Which one of these models you think is more suitable to go on with?
The high bias.
Why?
Because at least you're able to put all of the rain, all the clouds in one area. So now all you have to do is just find a way to change the location. With the other
Exactly.
one, you have to change the location and you have to change how much rainfall, stuff like that.
Okay, thank you very much. So the sad and bitter fact is that you cannot have a model with low bias and low variance. So this is ideal, but it's not gonna happen. This is terrible and you don't want to be there. So between these two, it's really the problem and your judgment as the modeler that tells you which one of this is better for you. Today and in the same lab, we've talked about 2 or 3 different examples that you may prefer one of them over the other one. Do we have any questions about these so far?
No.
All clear? As mud?
Wine.
Honey. Ooh.
Okay.
But what's
So-
clear, wine or honey?
I would say honey is also clear, but it has a magnifying effect.
Okay, so we pick
I
honey.
would say I don't want my glasses made of honey.
So they would be tasty though. Now here I have, okay, let's read this. In an ideal world, we want low bias and low variance, which we cannot have. When there's high bias error, it results in a very simplistic model that does not consider the variations very well. Since it does not learn the training data very well, it is called underfitting. For those of you who are going to be more involved with machine learning in the future, underfitting and overfitting terminology are going to become extremely common. When the model has high variance, it will still consider the noise as something to learn from. That is, the model learns the noise from the training data. Hence, when confronted with new or testing data, it is unable to predict accurately. Since in the case of high variance, the model learns too much, it is called overfitting. To summarize, a model with a high bias error underfits data and makes very simplistic assumptions on it. A model with a high variance overfits the data and learns too much from it. A good model is where both bias and variance errors are balanced. The balance between the bias error and the variance error is the bias-variance trade-off, a very hot topic in modeling. So, the irreducible error is the error that we cannot remove from our model or with any model. The error is caused by elements outside our control, such as statistical noise in the observations. A model with low bias and high variance predicts points that are around the center generally, but pretty far away from each other, very similar to Horace. A model with high bias and low variance is pretty far away from the bullseye, but since the variance is low, the predicted points are closer and in a cluster, similar to Darrell's. Bias and variance play an important role in deciding which predictive model to use, something that you will definitely learn more about if you go further in the field of machine learning and predictive models. The next question. How can we measure bias and variance? The goodness of fit metrics that we have discussed so far, MAE, RMSE, R-square, are they giving us any idea about bias or variance? Thank you very much for your elaborative answers.
I would say not, because it would only tell us how's the strength of the best fit line is, but I'm not too sure. I don't think it accounts the errors from what I think, but I don't know.
So if I want to convert your answer from a politician's answer to a student's answer, you are saying that the goodness of fit measures that we've worked on with so far do not tell us anything about bias and variance.
Yes.
Okay. Do I have anyone else that wants to give me something more?
Wait, does the mean absolute error give us something about variance?
What does the mean absolute error tell you?
Because it measures the distance the points are from the line of best fit.
Correct. So when you have a high absolute error, mean absolute error, you are basically telling me that
you have a high
your
variance.
observed are far from your linear fit. Does that tell you anything about bias or variance? Does it tell you about whether they are clustered or not? Does it tell you anything whether there's a high variance or not?
I could say a high variance.
Okay.
Potentially.
Maybe, yes. Anyone else? Okay. There are GOF metrics out there that we can use to measure the bias and variance of a model. For example, the Nash-Sutcliffe model efficiency and the Klein-Gupta efficiency. These are extremely useful when you are dealing with predictive models. The Nash-Sutcliffe efficiency is calculated as 1 minus the ratio of the error variance of the model time series divided by the variance of the observed time series. So it directly takes care of the difference in variance between predicted and modeled. In the situation of a perfect model with an estimation error variance equal to 0, the resulting Nash-Sutcliffe equals 1, NSE equals 1. KGE, on the other hand, provides a diagnostically interesting decomposition of the Nash-Sutcliffe efficiency. So it basically tells you 3 pieces of information about accuracy, about bias, and about variability. We're going to talk about that a little more. So, do you remember our example on TV, radio, and newspaper advertising? Okay. Let's say that we are interested to compare the performance of the linear models that use TV spendings and radio spendings as their predictor variables in terms of accuracy, bias, and variability. I'm going to first import my usual suspects, NumPy, pandas, statistics, and so on. I'm going to import my advertising CSV. You have this from last week. And I'm going to define my two NumPy arrays on TV spendings, radio spendings, sales, and I'm doing newspapers anyway, but I'm not going to use it for this example. So we're going to initialize a linear regression model using the stats model and using the OLS method for sales being predicted by TV. And then
I have a question.
Go.
What is that line model underscore TV equals SMF OLS sales TV? What is that doing?
Which part?
The whole line. What is the whole line doing?
This line?
Yeah.
Okay, so in this line, I'm using the OLS function from statsModel formula.api, which I'm calling SMF. And the way that it works, the syntax works, is that you first give a formula and then you define a data frame. Which data frame am I using? My DF data frame. What formula? I want to predict sales and I want to use TV as input. If I want to do that, that's how I write it. Sales. What was this?
Was it like tilde or something like that? Tilde?
And then TV. Did they answer the question?
So you're predicting sales using the input of TV.
Exactly. And
So
I'm
don't you
using the
have
OLS
sales?
method. Come again?
Don't you already have cells though?
Let me show you my data frame real quick. So this is how my data frame looks like. I have TV spendings, I have radio spendings, I have newspaper spendings, and I have sales. For a linear regression model, I need an input and an output, correct?
Yes.
So the question is asking us about linear models that use TV spendings and radio spending as their predictor variables, and they are going to predict or use sales as the output. So this is going to be my Y, and this is going to be my X for my first model. That's why I put sales tilde TV. Did you get your answer?
Yes, I suppose.
Awesome. So I'm naming my first linear regression model, model underline TV. And then the second one, model underline radio. It has the same setup. The only difference is that instead of TV, I'm using radio. And when I run it, now I have predictions based on my first model and predictions based on my second model. I'm going to calculate the RMSE for each model. And this is how I'm calculating my RMSE. I'm calculating the mean squared error, and I'm getting the second root of that, which will give me the RMSE. And when I run it, my RMSE for the first model is 3.24, and for the second model, it is 4.25. Which model is doing better?
The TV,
Why?
because it has a lower error compared to radio.
Exactly. The model that has the lower error has a better accuracy, or lower errors, of course. So let's calculate the R square, and we get these two values. The R square for TV for the first model is 0.6. For the radio model, it is 0.3. Which model would you pick?
TV.
Why?
Bigger.
Because unlike RMSE, when you're looking at R squared, you want bigger numbers. So the TV model is giving you a bigger number, so you're happier with it and you pick it. What about Pearson's R?
You would pick
What is this
the first
telling
one?
you? Why?
Because
Your mic is off.
you would pick TV
Why?
because they're both positive, so that factor doesn't count, but R is bigger.
Which means?
There's a stronger correlation, I believe.
Exactly. Yes. It means that there's a stronger relationship between the model predictions of the first model and the observed sales. Exactly. Thank you very much. So now we are going to do something new. I am importing the Hydro Eval package. You may have to install it if you don't have it already on your systems, but it's nothing different from the other packages that they've been installed. And do you remember this? What does this mean? When we say from a specific package, import this.
Is it the asterisk is a wild card, so it just imports everything?
Exactly. Yes, thank you. So I'm importing everything in that package. I'm using the evaluator function, and the syntax is like this. So NSE means that I want to calculate the Nash-Sutcliffe efficiency metric between the predictions of my first model and then the sales, the actual observed values. And then the same thing for the second model, the radio model. And when I get the number, I get this. What does this tell me? Which model would you pick?
TV.
Why?
Because it's bigger.
Because the ideal value of NSE is 1, and what we get from the TV model is closer to 1.
Yeah.
Okay. Now, my favorite metric, KGE, is basically calculated using the same function. Instead of NSE, we put KGE prime, and then model predictions and observed values. KGE, or Klein-Gupta efficiency, range from -infinity to 1. The closer to 1 you are, the happier you are with your model. It has 3 components. R, which is basically the Pearson product moment correlation coefficient. We already have looked at it. It has gamma, which is the ratio between the coefficient of variation of the estimations to the coefficient of variation of the observed ones. Again, the best value for this is 1. And then you have beta, which is the ratio between the mean of the simulated values and the mean of the observed ones. This is a metric of bias. Again, you are happy when you're close to 1. Now, when you run it for your first model, these are the 4 numbers that you get. The first one is your KGE score. Let's not think about that yet. What is this number?
Is it your R?
That is my Pearson's R, and as if you notice, it's identical to this number that I had calculated up there. So my Pearson's R is 0.78. What about my gamma?
The ratio between the coefficients.
And then 1?
The beta.
Beta. So that stands for my bias term. So let's compare these values from the first model to the second model. In every single comparison, we are getting better numbers from the first model, except for bias, which for both of them is ideal. So you can either judge and compare models separately based on these models, or look at this overall grade, the KGE metric, which is calculated based on these three. So which model would you pick?
TV.
Why?
It has better values for R and gamma.
Exactly, because you are getting a better, you're getting a closer number to 1 from the first model. Dr. Cleveland says, try this. Let me try it. So we are running KGE for TV and TV. So instead of observed, we are using the TV. Print TV underline KGE, of course. Now, as you see, we are getting ones. That is ideal.
And when that happens, let's see, am I muted?
Yes, we can hear you.
Okay, when that happens, your computer program has given you a very important signal.
You are wrong.
Farang, keep quiet. When you get that signal, what has your computer program just told you?
I did something.
You have the same. What's it called? Distribution.
Correct. You're comparing something with itself. That's what it tells you. When you get perfection out of any of your evaluators, you have screwed up. You've unintentionally put two series that you thought were different. One of them's identical with the other. That's not a bad thing to, it's bad if you stop at this point and say, well, my predictor's awesome at predicting itself. That's like the weatherman saying, I'm going to tell you what tomorrow's weather is day after tomorrow because I'll get perfect predictions. What it's telling you is you made an error and use that error to act upon it. The other reason I had him do this, when I use new stuff off the internet, because I do not waste my brain space on remembering how to do everything, because it's Python and it changes every hour, I sometimes have to run scripts with input like this to be able to understand what the output is supposed to look like with a good fit and with a bad fit. You may continue now.
Thank you. So, going back to the question that I asked at the beginning of the lab, how confident are we with our linear regression model? The 95% confidence interval for the forecasted value of y of x is calculated like this. The estimated value plus or minus a number. That's your confidence interval. Do you remember what we used to call this bandwidth before?
Margin of error.
Yes, thank you very much. The MOR, margin of error. Now, we are saying that we can calculate this SE with this formula. This means that there is a 95% probability that the true linear regression line of the population will lie within the confidence interval of the regression line calculated from the sample data. So we have a bunch of points. We fit a linear regression model somewhere. We can use these intervals above and below that line and say we are 95% confident that the true linear regression model, a true line representing the population, will be somewhere within these limits.
So technically in this way, before we were looking for, let's say, the margin of error for, let's say, the mean, but now we're looking for like the margin of error of the line of best fit.
Exactly.
Okay.
Exactly. You're looking for a range or a band that you will be 95% confident that the true line will be in. Are we clear on that? Okay. In the graph on the left of figure 1, this figure, a linear regression line is calculated to fit the sample data points, this line. The confidence interval consists of the space between the two curves, dotted lines. Thus, there is a 95% probability that the true best fit line for the population lies within the confidence interval, any of the lines in the figure on the right above. So within those limits, it can be any line that falls in there, but you are 95% confident that it will be there. So I have a question. If I increase my confidence level from 95 to 99, do you think this area is going to get tighter or wider?
Wider.
Wider.
I have 3 answers. Do you all agree with wider? Okay. So if I go from 95 to 85, what will happen?
Less
Smaller.
confident. Narrower.
So it will shrink down and it will get narrower. Thank you very much. Now, when it comes to linear regression, there is another concept that can be a little close to confidence intervals. This is called the prediction intervals. Here, instead of looking the entire line, we are looking at each specific point. So here we look at any specific value of x, x0, and find an interval around the predicted value of y0 for x0, such that there is a 95% probability that the real value of y corresponding to x0 is within this interval. So if it's a little too long, don't worry about it. Let's have a look at this. Let's say this was my observed value. And this was the estimation that I got from my model. So model output, observed value. I can calculate this band, get the upper prediction limit and lower prediction limit, and say that for this specific point, I'm 95% confident that the true value of this point will be somewhere in this band. So when we are talking about prediction intervals, we are talking about specific points. When we are talking about confidence interval, we are talking about the entire line. Wally, that is correct. So this is how we calculate the standard error of prediction and the prediction intervals. Before I go for the example, do you have any questions on this? So in this plot, in this figure, you see the confidence interval for the linear fit. And we are saying that we are, for example, 95% confident that the true line is somewhere between these two bands and within this limit. You good, Abby?
I'm good. It's just the last sip that I took from my sparkling water was so sour.
Okay. So, and in this one, we are looking at a specific point and we are finding a band or finding the upper and lower limits where we can be, for example, 95% confidence that we are capturing the true value. Any questions? Okay, now let us go back to this kind of a nostalgic example that we've been using for the past few sessions. We had some measurements of time and some measurements of speed. And this time, we are going to explore the confidence and prediction intervals for our linear regression model. First, I'm defining a list for my time. then a list for my speed, then I'm converting them to NumPy arrays. Now, we already know the parameters from last week, but let's assume that we don't. These were the numbers that we got from OLS and from MLE. So similar to what I did above, I'm going to create an instance of linear regression, and I am fitting it and get this. This is coming from OLS regression. You've seen this from Dr. Cleveland's lecture, so don't be terrified. Now, we are going to use the WLS underline prediction underline STD and calculate the prediction intervals for each point, the lower limit and the upper limit. When you look at it like this, it may not be as meaningful, but we're going to use this on a plot and you will see how useful they are. And then through this, I am also calculating my confidence intervals, lower band and higher band. So if I plot this, this is quite familiar for you, right? Blue points, red line. This is the fit that we got from our linear regression model, and we used the Harper Hill method to describe it over lower values, higher values, mid values. Do I have anyone in the room who do not feel completely comfortable with this plot? I know Dr. Cleveland doesn't like this plot because it has no labels on the x-axis and the y-axis, but none of you even noticed it. Shame on you.
There are no titles.
So let's say that on the same plot, I want to add the lower prediction band and the upper prediction band. Now, what does this mean? For example, for this point that I'm pointing at, what is the meaning of these green dashed lines? I want a volunteer to come out and help me.
The dashed lines would represent the lower and maximum possible of the point on the, of the point.
I want you to repeat your answer in a slower tempo so that we can all understand it.
The dashed lines represent the probable positions of that point.
Okay.
Because we're giving the margin of error for the line.
Based on?
Oh, based on
the
blue points.
The margin of error.
Mod.
Based on the model that we got from our samples, we can pass that judgment.
Oh, okay.
You forced Dr. Cleveland to drink water. That's how much pressure was on him. So for every point that we have, we can use these lines to get an understanding of where the true value might be based on our model. Now, let me hash these again. And this time we are going to look at lower and upper confidence bands. Now, what do these orange lines tell us?
The orange lines are based on the line, right?
Yes, everything that we are doing is based on our model, which we have created based on our samples.
Maybe it represents the range of the line, like the points of the coordinates, or
So at this point, you do not really have to look at the blue points anymore. We have a red line, and we are using those upper bands and lower bands to say something with 95% confidence. What are we saying?
Oh, the confidence interval that we're 95% confident that the line will be in that area.
What line?
The line of best fit.
I get that. Okay, I give it to you. We have already created the line of best fit based on our blue points. So the red line is there. The orange lines of that bandwidth is telling us that we are 95% confident that the true linear fit of the population will be somewhere within these limits. Now, it can have a different slope, it can have a different intercept, but it will be somewhere between these orange bands. Okay? Are we clear? A yes would be good.
Yes, sir.
Yes.
Okay. Now, this will be the full-blown plot that gives us the prediction intervals and the confidence intervals for the line that we have. So the next time when we give you a question, either in an assignment or in an exam, and we ask for a linear regression model, you do the red line. When we ask for the prediction intervals, you add the green lines. When we ask for the confidence intervals, you give us the orange lines. Do you have any questions? Okay, so here are some of the blog posts that I used for this notebook. Here are some interesting reads and videos that you can enjoy on the same topic. And as the exercise for today's lab, I've asked you an ideal model. Why not? Why do you think we cannot achieve low bias and low variability at the same time? So you can Google it, and there are some answers for you out there. That's it. If you have no more questions for me, I am going to stop sharing my screen. Thank you for your attention. And special thanks to those who played the games with me, and pass the host back to the boss. All yours.
Okay. I will take 4 minutes to complete what I was trying to do earlier. So what Farang just showed you, you just made green dashed lines and orange dashed lines. The orange dashed lines conveyed to us that are like, we have 95% chance that the red line that explains our data will fall in those orange lines. The red line is just one of an infinitude that could explain our data, and the 95% probability of that infinitude falls between those orange lines. When we go to higher dimensions, life gets a little bit trickier. For one thing, you have to load in all the software. So here was my earlier example with abrasion resistance, and I had you remembering pictures. Well, now that I've got it to work correctly, look at our R squared in this case with only a single predictor, and that predictor happens to be the hardener. So if you look at just the hardener, versus the fiber addition, it's clear using R squared as a metric that the hardener is a much greater contributor to abrasion resistance than fiber. Let's then go add both variables. That was our model number 2 in the write-up. And we get some improvement by adding the second variable. Now let's go ahead and plot it. So this is what I mean by trying to do a Harper-Hill method of explaining multidimensional results. We see that the plane kind of sort of maybe passes through the blue dots, but there is quite a bit of gray space between the blue dots and the red plane, and they're over the same x1, x2 domain. Then we'll add our other variables, which are just products of x1 and x2 and the various ones squared. Do the fit. Our R squared is like awesome now. It's practically at 1. So we're ready to go home and drink mint juleps and celebrate our awesome model. And then when we plot the curved plane and the blue points, visually, that kind of looks better, but the point we're illustrating here is, so what if it looks better? It's really hard to tell if those blue points are falling on the plane or not. So in higher dimensions, we are sort of, well, we are almost required in higher dimensions to use these goodness of fit tools, because our human brain can't resolve that picture. I mean, that's not bad. If the blue points were all up here, we would clearly mentally say, well, that's a terrible picture. And then the next cool thing would be to make it a homework assignment to have you figure out how to fill in the plane with a 50% shaded red surface. But I'm looking at the video and everyone's going, no, don't do that. It says you're free. No, I won't do that. So I have saved that, and that was what I was trying to show this morning. So with that, I will end today's phone call. I want to thank you all for your patience. I want to thank Farang for my favorite lab of all of them with Horace and Daryl. Because if you can talk to Horace, you could probably convince him to shoot the king and then or shoot the judge and then escape. We need to do a fistful of dollars version of that lab someday, where you have to shoot the rope out of anyway. Have a good afternoon, everyone. Have a great weekend. You have labs due next week. You have assignment due this week, and you'll have assignment due next week. And next week, I think, is when we start introducing the group project. And Farang and I will work together over the next few days to go ahead and figure out how to do the groups for the project, because I think we're getting to that time of the semester. I want you to have enough time to work on it. So with that, everyone, so long. Have a good afternoon. Have a good weekend. Bye-bye. Be safe.
The group projects.
Don't take any wooden nickels. Try to avoid killing kings so you don't have to depend on Daryl and his other brother Daryl to save you.